Let me ask you a question. Do chemists have a global or social responsibility to think about when they are making molecules? Stay tuned. I'm going to show you the 12 principles of organic chemistry that you need to think about as you become a chemist. Hey there, OChemNinjas. Chemists have a big responsibility. We have a lot of solvents and reagents and chemicals at our disposal, and there's a very thin line that we can cross as we reach across the stockroom shelf. Which chemicals we choose to use in our reaction can make a difference. It would not be totally unfair to say that chemistry of the past used to have the motto, make the molecule no matter what the cost. That cost could be financial, the cost of procuring the reagents, but there's also a cost to health and safety. Some reagents are more toxic than others. There's also a cost to the environment. Some molecules are persistent pollutants. The next generation of chemists is encouraged to think about green chemistry principles. We are encouraged to change the motto to make the molecule while thinking about the costs. There will always be costs. There will always be pros and cons to any chemical process. It's our job as chemists to look at a risk matrix and decide, is this the best reaction that I could be performing? In 1998, the 12 principles of organic chemistry were proposed as a framework to think about how we future chemists can perform chemistry. The first green chemistry principle is just prevention. It says that it is much better to prevent waste from the start rather than trying to treat it or clean it up after you've made it. Some might say this is the guiding principle from which all the others are derived. Two common quantitative metrics that we have come up with to assess prevention include the E factor. It's a factor of the mass of the waste produced in a process to the mass of the product produced in a process. You would want this number to be as small as possible. When you factor in the amounts of solvents that you need and all the different processes that you have to go through on a large scale to do a bulk chemical process, E factors tend to be in the range of 10 to 60 or so. And it's our job as chemists to try and lower that E factor as much as possible. Another way to assess this is the process mass intensity. How much is the mass of the inputs compared to the mass of the products? How much stuff do we have to dump into the reaction just to get out the thing that we want? We would, again, want this number to be as small as possible. The second principle of green chemistry is atom economy. Atom economy looks at the efficiency of a process. How many of the atoms that we put into the process make it into our desired product? We quantify that by looking at the molecular mass of the product divided by the molecular mass of all of the stoichiometric reagents. For atom economy purposes, we do not include solvents or catalysts in the denominator of this equation. Ideally, every single element of all of the reactants would incorporate into the product. And there are a few reactions that have 100% atom economy. The Diels-Alder reaction is a good example. If your molecule has some kind of leaving group that gets discarded as a byproduct, that cuts into your atom economy. If you have a large, heavy reagent, but only a small portion of that reagent gets incorporated into the product, the rest is lost as a byproduct, and that cuts into your atom economy. Green chemistry principles 3 and 4 can be combined together in less hazardous chemical syntheses and designing safer chemicals. Early chemists just didn't know what impact their reagents had on their health. As such, many of the bedrock reactions we learn in sophomore organic chemistry use some pretty nasty reagents. These reagents are very good at doing the reactions that we need to do. These solvents are very good at dissolving the things that we need to dissolve, but they're pretty hazardous to our health. These green chemistry principles encourage us to think about these reagents that we're using and try and minimize the health hazards and toxicity, both toxicity to us as humans and toxicity to animals and the environment. As the field of toxicology has developed in parallel to the field of chemistry, we can really start to work together to test a lot of these reagents to make sure we're having the impact that we think we want to be having. Green chemistry principle number 5 encourages us to choose safer solvents and auxiliaries in our processes. The solvents are the things that dissolve the reagents in your reaction. When we talk about auxiliaries, think about the reagents and solvents that you might use for a liquid-liquid extraction or for a recrystallization or filtration. The goal is to make those solvents as innocuous as possible or eliminate them completely. Solvent-free organic chemistry reactions is a legitimate field of chemical research. There are tables that you can look at that will list solvents that are particularly hazardous and suggest a greener alternative to that solvent. Ideally, we would be working towards benign solvents such as ethanol or water. Water is a tricky one. It would be a really nice solvent, except that most reagents in organic chemistry are not soluble in water or would be quenched by water. So get to work, future chemists, on developing water-safe organic chemistry reactions. Sometimes chemists will say, who cares about the solvent? It just goes under the arrow. Nobody really cares what the solvent is. But think about it. Solvents will account for 50 to 80% of the total mass of a given process. They are often a large draw of energy in a process as well. These solvents we use will need to be heated up or boiled or distilled or cooled down or vacuumed away or mixed And then when we're done with them, maybe we'll send them off for recycling, but more often than not, they're going to be incinerated. We are always going to need solvents, but can we do a better job developing new reactions with benign solvents? Green chemistry principle number 6 asks us to design for energy efficiency. Depending on the thermodynamics of the reaction we're doing, we often need to heat up or cool down reactions. We often need to distill solvents away or heat them up for recrystallization. Even using your little magnetic stir bar requires an energy input. This principle encourages us to consider our energy load in our reaction processes. Maybe there's a catalytic version of a reaction that you could develop that would not require a reflux. We often get so caught up in the reagents or the separation or increasing the yield that energy efficiency is sometimes a forgotten green chemistry principle. Green chemistry principle number 7 asks us to consider the use of renewable feedstocks for our starting materials. There's no great way to sugarcoat this. Most organic molecules come from crude oil. We refine crude oil to make bulk commodity chemicals, and we take those commodity chemicals and we derivatize them to make the variety of chemicals you can purchase from the chemical supply company. But what if there was another way? What if we could derive those starting materials from plants or algae or bacteria and make those molecules from thin air, from the carbon dioxide in the air? That would be a more renewable source of those starting materials. There has been a lot of really good groundbreaking work in this field. We hand this over to you as the next generation of chemists to see if you can improve on these methods and make a larger variety of chemicals through these renewable means. The next green chemistry principle really cuts me as an organic chemist. I feel like this green chemistry principle is targeted towards organic chemists specifically. Green chemistry principle number 8 asks us to reduce the use of derivatives in our syntheses. In a classic sophomore organic chemistry question, you might be asked to add an ethyl group to this molecule. The problem is there are 2 acidic functional groups in this molecule, and you only want to react with the alkyne. So, as every sophomore organic chemist knows, you protect the alcohol as a silyl ether protecting group. That gets rid of the acidic proton on the oxygen, so you can derivatize the alkyne and get your alcohol back with a deprotection step. The problem is that every atom in that protecting group ends up being lost as waste, and we talked about waste prevention in previous green chemistry principles. This is a big source of waste, a big source of time and energy and loss of efficiency in a chemical process. As chemists, we are called to develop new reagents that can react chemoselectively, that can react with one functional group but not another functional group, that could react with the alkyne but not the alcohol. Or more broadly, what if you had 2 different alcohols in the molecule? Could you react with one of them but not the other? As you progress in organic chemistry, as you take an advanced organic chemistry course, there are a library of chemicals that can do chemoselective transformations. But if you want my opinion, I think the future is in enzymatic reactions. As we enter into a new era where we can design specific enzymes for a specific function, I suspect we'll be able to design enzymes that could do this transformation without the need of protecting groups. In fact, I can imagine a future where the new blockbuster pharmaceutical drug is made completely in enzymatic reactions, where every enzyme has been custom made for this particular pharmaceutical drug, and the molecule just kind of walks down the line from enzyme to enzyme, and we get the pharmaceutical drug out the other end. So, get to work, biochemists. Make me proud. Green chemistry principle number 9 asks us to include catalysis as often as possible. Catalytic reagents, especially if they are very specific, are superior to stoichiometric reagents. A classic sophomore organic chemistry reaction you've likely learned is the dihydroxylation of an alkene with osmium tetroxide. This is a great oxidation reaction. It's just that osmium is exceedingly toxic. It can react with all the double bonds in your retina and cause you to go blind. So chemists have developed a catalytic version of this reaction. We can do a catalytic version of this reaction with a catalytic amount of osmium tetroxide if we include a stoichiometric reagent that is much less harmful. Green chemistry principle number 10 asks us to design for degradation. We started off looking at the inputs into a reaction. Can we optimize those to be as green as possible? Then we looked at the process itself. Can we make it more energy efficient, use less solvents, and safer catalysts? Now we have to think about the molecule we're actually trying to make. What is the long-term fate of our ultimate product? When this goes out into the world as a bulk chemical, what's going to happen to it? Is it going to leach into the soil eventually and become a persistent pollutant? Is it going to run off into the waterways and become an aquatic hazard? Design for degradation means that when we make our product, we want to incorporate enough functionality in it that when it releases into the environment, it will break down into benign byproducts in a relatively quickly manner. And that's hard to do. We expend a lot of effort designing the molecule to do its original function. To add another level of complexity to also design it to degrade adds extra complexity to our chemical processes. But I have trust in you, future chemists. I know you can do it. Green chemistry principle number 11 employs real-time analysis in our chemical processes. We have so many sensors and gadgets on our cars as we drive down the road, we can monitor pretty much everything about our surroundings at any given time. Let's do the same for our bulk chemical reactions. Can we monitor the temperature to make sure we're not getting an exotherm? Can we monitor the pressure to make sure that the pressure is not building up too high? Can we monitor the rate of product formation so we can stop the reaction as soon as the product is made and not run it for longer than we need to? Can we monitor in real time the amount of byproducts that are made so that we can alter the synthesis to make less byproducts? This one is where analytical chemists really shine. There are a variety of analytical chemistry techniques that we can employ in real time to monitor our reactions to make sure that they are safe as we think they are. The final green chemistry principle is the logical outcome of the first 11. We want to have inherently safer chemistry for accident prevention. We want to choose materials that minimize the accidents and leaks and explosions and fires. We really can't employ green chemistry principle number 12 without using some of the previous 11 principles. If we can make products that are safer for the environment, they're also likely to be safer for the general public. But that also means they're likely safer for an unrecognized class of workers, the people on the line at the bulk chemical processing facilities that are doing this chemistry day in and day out. They deserve to have safe working conditions. As we think about those other 11 principles, this 12th principle will make chemistry safer for all involved.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.